Okay. What's qualitative data? Using observations. Okay, using observations. Very good. Now, with the qualitative data, there are two. With the qualitative data, there were two things that really hit on yesterday. One is that I wanted you to be detailed. Okay, blue is not blue, bubbles are not bubbles. We want you to be detailed with that, within a reason. You don't need to write 3 or 4 pages on all the detail of every step of what you did. Okay. Two, the qualitative data, depends on what you wrote down, can really save you with your post-lab. So if you have some error going on in your post-lab stuff, you can come back to your qualitative data. Most of the time, something in there is going to help you defend why your data, why your post-lab wasn't that good. Okay? So that means that not only are you using your senses for the actual reaction, but also what's happening around you. Right? So yesterday we talked about if my partner and I, if we spilt or broke something and we lost mass or something, and that's recorded, all right, it's recorded in our data, I can use that to support why my post-lab wasn't that good. But you can't use information that you didn't write down. Okay, you can't make, well, I think this happened, so I'm going to use this instead. Okay? Side note on that, though, too, you could use logical reasoning. Logical reasoning you could also use to defend why your percent error might be bad. Okay, but when we get into our labs and so forth, we'll come back to that idea, right? But for the test on Thursday, make sure you know the two types of data, the differences between the two. I might even ask you to give me an example of qualitative data, an example of qualitative data. So you would not say grams for quantitative data. Grams is a unit. You might say 9 grams or 15 milliliters. That's a measurement. Okay. You might say navy blue solution for qualitative data. You might say smells like skunk would be a qualitative observation. All right, did we get into the periodic table yesterday? Okay, so let's start with the periodic table. I'm just going to give you some basics on the periodic table. We've already talked with about some of the information already, but just some very basics, and then we'll go and get into the last lesson of nuclear stability. We've already established that the periodic table is a tool in chemistry. You've already used it as a tool. You'll hunt and you'll find the names of elements, the atomic number, identify elements already, the atomic mass, mass number. So you're already hunting and using that as a tool already. So that's awesome. Now, the periodic table is set up a certain way. Okay, it's set up with horizontal sections, which we call rows or periods. So we're going to use that verbiage, row, we'll say period 5 or row 5 or something like that. So rows or periods, that's the horizontal or the left to right. So as we go left to right on the periodic table, we call them rows or periods. Now, next to the periods, we have these numbers. There's 1, and 2, and 3, up to 7. So we have 7 of these numbers. Anybody have an idea what these numbers are called next to the periods? Numbers next to the periods? Don't think too hard. What's that, Zach?
Periodic numbers.
Very close. They're called period numbers because there's numbers next to the periods. We call them period numbers. I know. Don't miss out on the test. That's an easy one. Period numbers. Okay? The vertical, the up and down portions on the table are called columns or groups or families. So this would be column 1A or group 1A or family 1A. Okay? So groups, columns, or families. You see that quite a bit. Now we have numbers above the columns. What do you think the numbers are called above the columns? Column numbers. Whoa, column numbers, okay? So we have a 1A and a 2A and a 3A all the way up to 8A for those. We do have column numbers for this middle section, but we're not going to use them in high school chemistry. Okay, so we can kind of ignore these values here. But every column has a column number, and then every row or period has a period number. Okay? Why do you think we call them families? What's so special about family? How many have been to a family reunion? A couple of, okay. What are some of the common phrases you hear at family reunions? You look just like your dad. You look just like your mom. You hear that quite a bit? Why would they say that? You sound just like your dad. You laugh like your mom.
I love you.
I love you. Oh, thanks.
You hear that? It's been a while.
You hear that? Oh, I thought you were telling me that. It's kind of weird, man.
That would have been really weird.
That was kind of weird. Right back at you. Hey, here's a peace symbol. All right. Stay calm. Treat him like a friend. All right.
That was strange.
So, we call them families because within the family you have similar characteristics, right? You might, in your gene pool from biology, in your gene pool, you have a certain characteristic and properties that are kind of meshed together. So at these family reunions, and how many of you look like your parents a little bit? Well, yeah, a whole bunch of us do, yeah. All right, okay? So that's why we call them families, right? Because they have similar properties and characteristics. Remember sodium and water? How does sodium and water behave? Very explosive, right? Catches on fire, boom, explodes, okay? So do you think lithium might behave a little similar way? It's in the same family.
Sure.
Yep, sure. How about potassium? Yep, sure. Actually, potassium is a little bit more aggressive. Right. Rubidium? Yep, a lot more aggressive. Cesium? Even more aggressive. So as we go down the families, that property for group 1A gets more and more established. So cesium actually has to be kept in a steel, in a airtight container, usually a glass container, because the moisture in the air would react with it and cause it to explode.
So
Yes.
1A is a family, then 2A is a different family?
Yep.
And then it just keeps going?
Yep. So each column is a separate family.
Okay.
What is the bottom one?
The bottom one, francium.
Yeah.
So francium is radioactive, so it's not really in existence enough to kind of capture.
Okay.
So we just kind of stop with cesium. And if you go on YouTube, you'll look for cesium in water. You'll look for people blowing up bathtubs with cesium. They'll throw a glass vial with cesium in it, and they'll throw in like a rock or something with the weight come in, it'll come down, shatter glass, and yeah. If we had cesium, we might do that, but we don't have cesium. It'd be a great demo, wouldn't it? Yeah. It'd be like, here, hold this. Blow your hand off, it'd be kind of cool. My hand's melting.
You can do Mentos and pop.
Yeah, we have to use a shower for that for it. Yeah, it'd be kind of cool. You thought Pop Rocks were pretty potent, right? You had the candy about that we call Pop Rocks, right? All right. Yeah. Let's put a little cesium in there, just a little bit. Just a little bit. Yeah. Yeah. A little punch. A little extra punch in your mouth there, yeah. You'd be bleeding and holes through your tongue. Not good. Oh, there you go. That'd be a good test object on a cat, wouldn't it?
You guys saw Mentos and pop? What do to cat?
Oh yeah.
Yeah. Same thing.
All right, so these families have names. We're going to work on 4 of them. So group 1A family are called the alkali metals. That is their family name, the alkali metals. Alkali metals. And we need to know that they are the most active elements. The most active elements of the alkali metals. A lot of times when we think about metals, we think of wire, something kind of hardcore like this shelf here, something hardcore, okay? But for the alkali metals, the cool thing about them is that they're pretty soft. You can cut them like butter. Take a knife and just cut right through it. Okay, like butter. Yeah. It's very soft metals, cut with a knife. Then we have group 2A. We call these the alkaline earth metals. Alkaline earth metals. How many of you have heard of the alkaline batteries? All right, 2 of you, okay. The word alkaline means basic. The word alkaline means basic. So if you were to put an alkaline earth metal in water, it would form a basic solution. So the pH would increase. You would have a slippery, slimy kind of feel texture to it, kind of greasy. That's a characteristic of a base. So alkaline means basic. All right, just fun factoids. They're not as soft as the alkaline metals, they're kind of cousins of each other, but they still can be cut, you can still cut through them. A pair of scissors can cut through them, a knife can cut through some of them. So I could have you compare and contrast group 1A and group 2A. Then we have 7A called the halogens. Halogens. Well, we used to have names. We used to have names for these, like this is the chalcogens. Used to be called the chalcogens, but then they kind of phased those names out, so they don't have names anymore. So we would say the boron family, the boron family. We would say the carbon family or the nitrogen family. So they kind of changed those. But the other 4 families that we've kept those names intact. And I don't know why they've let the names go. Not part of that process. So 7A is called the halogens. And the cool thing about the halogens is that halide means salts. Sodium chloride, chlorine is a halogen, fluorine is a halogen, bromine, iodide, potassium iodide is a halide. If you've taken geology or even earth science, sometimes you have to identify minerals. How do you identify a halide? Don't they do it in earth science anymore? They identify minerals, right?
Oh, yeah, they're doing it right now.
Okay.
I have the next one.
Sweet. So how do you identify a halide?
Oh, no, I just know the word identify.
Oh, so you lick it. If it tastes like salt, it's a halide.
Probably we're supposed to lick things.
In chemistry, geology is a whole new world.
You can lick those.
You can lick geology, people. Yeah, I don't. All right. And the last group we call the 8A is the noble gases. We all know this and love them. Noble gases. And something special about the noble gases you learned back in 8th grade is what? What do you remember from the noble gases? All stable. Okay, which means what?
They have like a completed ring on their outside, so they don't need any extra or any less electrons.
Okay, so the noble gases have a complete energy level, all the electrons that it needs it has, okay, which makes it unreactive. So a good vocab word would be inert or non-reactive. Some of you are inert on Monday mornings. All mornings. Some of you might be inert at gym class maybe.
Yep. I feel that.
All right. Sometimes you're inert in this class. I don't know. Sit up front.
I fell asleep once in my grade.
Oh, yeah. Okay. That's all we need to know for periodic table. A lot of factoids on that one. Now, from this point on, I would normally go into the historical perspective of the atom. We would talk about when it first was derived, back Age of Reasoning, 400 BC. We would go through the historical perspective of... Why not? Let's go. John Dalton. I might come back to John Dalton a little bit later. Then we would go through the scientists that... right. So this is what we used to do, but we're cutting some of the curriculum out to fit. No, the state just says. If I was not the state, I would give you the whole thing. But the state says I got to teach it, so I got to teach what?
We're all thinking it. Why would we free for that?
I have students that are absent today, and so they email me and ask me if I would video the lesson. So sure.
Bruce,
I just want to look fancy. Do I look fancy with it on?
He's wearing a wire.
Yeah.
you put the hairs on there?
What's that?
When you post this, will we go with Jamie on there?
Depends. They might be able to pick it up. Yeah.
Hi!
They don't hear anything else here.
Deborah. Then we have scientists that kind of prove that the atom does exist. So we have something called JJ the Jet Plane Thompson. I made up little nicknames for him. JJ. Remember JJ the Jet Plane?
Yes.
Yeah. What was that?
No?
All right, little cartoon, little plane cartoon.
Yeah, there's a little.
My kids used to watch them a little.
Or Caillou.
Caillou, yeah. I don't have one. I don't have a nickname for Caillou though. And then we have Robert the Milkman Milliken.
Robert the Milkman Milliken.
It's like a wrestling name. Ernest Goes to Camp Rutherford. He- Ernest Goes to Camp. We've seen. All right, man, you guys are in tune. Last couple hours, there's like this generation gap. They had no idea what I was talking about.
Ernest goes to camera.
Yeah, it's good stuff. So Rutherford actually worked with radiation that you read about over the weekend. So we'll come back to these types in our notes today. Guilfoyle experiment, pretty important. We'll come back to that later. Now we get into nuclear stability. Okay, this is we're going to camp out. This is our last lesson. So we're going to talk about what nuclear stability is. Then we're going to apply it to writing nuclear equations, and then we're done. Okay, so our goal is to get that far today. Give you some homework tonight on top of your quiz stuff for tomorrow. And then whatever time we have left tomorrow, you can ask questions about the test or about the study packet, that sort of thing. Okay. What?
That's slapstick comedy right there.
So I'm not going to use the PowerPoint for this. I'm just going to kind of talk through and explain. Bright lights, bright lights.
No, worst thing is getting out of school and then going in the hallway at like a hotel. Super dark. No, it's super cold. Not dark.
Okay, so first of all, what do you think we mean by nuclear?
Fission or bombs.
Nucleus.
What? Bombs, okay. All right. Nucleus, all right. So when you see the word nuclear, we are referring to the nucleus. Well, a nuclear bomb was a pretty good answer, yes. But nuclear refers to nucleus. Now, what does stability mean? We refer to.
Stable.
I gave you the word.
It's right there.
Nuclear.
What does that mean, stable, though?
It means that it's not dangerous.
Not dangerous. Well, we'll go with that.
You want to hear a fun fact?
Sure.
The first high five happened in, take a guess actually.
1962.
Close. Anyone else?
You're like people like each other's hand all
1949.
1977, two Dodgers players did it by accident.
Thank you for that.
Want to hear another one?
Well, give me the accent. I want to know.
Oh, like they didn't even go into details. I forgot their names, but if they scored a run, they accidentally high-fived each other. So I don't even know. Honestly, it was.
Maybe it was a miss
it's like
handshake.
actually true, like,
Went
yeah.
the handshake instead, it was a tap. And oh, hey.
I thought it was gonna be like 1,500 or something like. No,
Sure,
it was
no,
like
okay.
17.
I wouldn't name it
Yeah.
high five, I'd name it after myself.
Yeah. They must have been high and
Ryan's like,
up by 5.
Wait, what if
There you go. There you go.
They actually did it down here?
The other one, this
Why would
one's a
we
crazy one.
All right.
If you fold like a regular piece of paper in half 42 times, it would reach the moon. That's actually true. So was the last one, but that one's true. In half. Like if you fold it in half, you can't do it.
How big is this? How big? Like 8.5 by 11
Like,
sheet?
it's just a regular like blank piece of paper, and you fold it in half 42 times, it would reach. They have numbers for it too.
Because
Like
it would
how tall
double
it'd be.
42
What class did you just send this in? Because I learned that last year.
I don't know what class it is.
So I can unfold it and then I can reach the moon?
Yeah, just climb on.
No, there's no way a standard piece of.
No, I promise you, it's actually, they have numbers for it and everything, it's exciting. It's like, NASA put it out.
It would
Has
make
to
it,
be true.
it would make it so small that it could make it look.
Like, it'd be, you can't do it. Yeah, you can't actually do it,
You
but,
can't even fold paper 7 times.
no. I think 6 is the maximum or something.
All right, good tidbits. That's good. All right. So
Is your video still going?
it is. So I apologize for those who are in absent. So Mr. Fish has to listen to you guys. All right. So nuclear stability. We want to focus on the nucleus, not the electrons. So on the nucleus, and we want to understand why it's not dangerous or how it's stable, or sometimes unstable. Okay. So that's our focus. Okay. So let's look at the nucleus. What do we know about the nucleus of an atom? No, doesn't store energy. Protons and neutrons. So let's focus on the protons. Okay, so I'm going to put these positive symbols up here, if that's okay, to represent protons. We're good with that?
Looks like Jason.
Sure.
Gary,
Okay. So in the nucleus, we have these positive protons. In the nucleus, we have these positive protons. If I just look at just that, you should think of something because they're all positive particles. Positive particle protons. What should come to mind? They're all positive particles. What's that? Not cations, the positive particles, not positive ions, positive particles. What do you know about positive particles? You get a bunch of them together.
They don't want to be together. They want to stay as far away from
They want to be away from each other as possible, right? Coulomb's law,
bunch of tension.
right?
You gotta put some negatives in negatives. That's what they're called.
Okay, so because the protons are positively charged, they're going to create a repelling force. A repelling force, because like charges repel, unlike charges attract. Like charges repel, unlike charges attract. So all these positive particles are going to push away from each other. So they are creating tension. Okay, that was a good word. How many of you know what anthropomorphic means? Anthropomorphic. Anthropomorphic.
That word before, I know what it means. I don't forgot.
So when you say an atom is happy, that's anthropomorphic.
So it has the same amount of negative and positive charge.
When you say something is a rock is happy, my pet rock is happy. It's anthropomorphic, meaning you're giving an inanimate object animate characteristics.
Personification.
It's part of it. Okay, anthropomorphic. Okay, so I might use that use it in here. Okay, I might use some of that to make this work. Okay, good. So the protons are creating this repelling force, and I like the word tension, so I'll put that off to the side. Tension. So you can think of a balloon. If I blow a little air into a balloon, my balloon gets a little bit bigger. And then more air, more protons, it gets bigger. More air, more protons, it gets bigger. More tension. Okay? So the protons are creating this repelling force, this tension. How many of you have seen the movie Apollo 13?
Oh, is that with Tom?
3 of you.
Is Tom Hanks in
My
it?
dad's.
Or is that Apollo 11?
I think that one's Apollo 11. Apollo 13 is the one where they try to go to the moon, they don't quite make it. They have some issues, like when they took off from the rocket, something fell off from the rocket going up, or from the space shuttle, and when they got there, there's some things that were wrong. So they had to abort the mission and come back. Pretty bummer, okay? I don't think he's in that one. So as they're coming back, though, they're having issues coming back. One of the issues in the movie talks about a CO2 filter it went bad in the shuttle, which means that the filter can't filter out the CO2, so now they're starting to get CO2 poisoning, and they can die. So one of the scenes shows in a small room table about 8 scientists, 8 physicists, okay? A guy comes in with a box, throws a bunch of equipment on the table and says, hey, this is what they have up there in Space Shuttle. You have to figure out how to make a CO2 filter that they can build up there so they can survive. Oh, and by the way, it has to be done like yesterday because this is happening up there right now, okay? So no pressure or anything. Now, a lot of scientists are known to be type A personalities. What's a type A personality? Give me, what's that? They are perfectionists. What else do you know about type A people?
Smart.
The smart, what's that? More hyper, okay?
Like actually more hyper. But not, okay. I got it.
So type A people are aggressive, perfectionists, OCD to the end, okay? At times can be very hard to work with other people. My way's the highway.
My way. So what type B would you?
Even if I'm wrong, my way's the highway. What's that?
My wife.
Why would you want a type A person? Because they are perfectionists. They do things high quality. It's going to get done in a great way.
If
So
somebody
okay.
told them what to do and they disagreed, would they take their way? Like,
Wait, what about
not?
They might think it's a different way. They'll probably still get there.
is type B the
Right.
opposite? Type B is just the exact opposite. No?
I don't know, who are my psychologists?
Type B is probably. Type B is
Probably,
more go with the flow kind of.
yeah, kind of.
Is there a
Yeah.
type C? No. I think I'm more of a type Z type.
Type Z, yeah. Type G, Gannon, type G. Yeah. Now, back to our analogy. In this room, our 8 scientists are all type A people. Can you imagine the tension going on inside that room? Okay? Nothing's going to get done. All right? It's like these two just getting after it. Just, oh, it's going to be a fist fight. They're just getting after it. So that's my analogy here. Inside this nucleus, we have this tension. All right, this tension, this anthropomorphic thing of people just getting after it. This very tense going on. So with that in mind, then, what keeps the nucleus from exploding or doing something dangerous or being stable if this is happening? What else is in the nucleus? The neutrons. Okay, the neutrons. So we're going to put neutrons in here. Neutrons are neutral. Well, that doesn't do anything because if we think if they're positive, they would kind of negate the repelling force of the positives, or if they were negative, but they're not. They're neutral. Okay, well that doesn't help us any. Well, neutrons are like your mediators. Okay, so Ryan's a mediator. He's going to come over here, a peacemaker. He's going to come over here and say, "All right, you two work together. She's okay, you're okay, we're all okay, we got the same problem, we got to help them in the space shuttle, let's work together." Okay. All right, so they're the peacemakers. They're going to come in, they're going to calm down the tension with this repelling force. Okay, again, that's my anthropomorphic connection, okay, personification connection, okay? But what they really do is this. These neutrons are going to create a force of their own. They're going to create a strong nuclear force. Okay, they're going to create the strong nuclear force. We don't know how. They just do. The strong nuclear force of the neutrons are going to stabilize this repelling tension force of the protons. So these two forces are going to battle back and forth to keep the nucleus stable. Okay, that's the simplistic view of nuclear stability. So we understand what's going on inside the nucleus. Tension going on. Okay, just combating back and forth. Okay? Now, here's what we have to understand. The stability of the nucleus depends upon the proton and neutron ratio. This would be a good test question. What does the stability of a nucleus depend upon? Answer, proton-neutron ratio. Can you read it okay? I can rewrite it. Is that legible? Okay. All right. So get a periodic table out. We're going to look at some ratio stuff here. We're going to, in your reading, you looked at the what's called the radioactive belt, the graph with that. So let's look at carbon first. Look at carbon. Pretty easy. What is the number of protons that carbon atom has? 6. And neutrons? 6. So the ratio is 6 or 1 to 1. So for every proton that the atom has, it only takes 1 neutron to neutralize or combat the two forces. Okay? How about fluorine? 9 protons and roughly 10 neutrons. So still pretty close to 1 to 1 ratio. All right. How about magnesium? Protons? 12 and 12. So again, 1 to 1. All right. I see a little trend going on here. Silicon? Protons? 14. Neutrons? 14. Oh, I see a trend. Calcium? Protons?
20.
Neutrons?
20.
Okay. So elements 1 through 20 have approximately a 1 to 1 ratio. Protons, neutrons. And they're all stable. All perfectly stable. So what happens when we go beyond 20? Look at gallium. It's got 31 protons. Neutrons? 38. So the ratio starts getting away from the 1 to 1. Okay, it's getting a little bit bigger. Let's look at strontium. Strontium's got 38 protons, and then how many neutrons? No. 49? Okay, so see how the ratio is starting to increase a little bit more? We're having a lot more protons, but now we need more than 1 to 1 ratio for the neutrons to make that stable. Okay, look at mercury. And mercury, yeah, mercury. How many protons? 80 protons. Oh my word. 80 positives inside a nucleus. Can you imagine the tension going on inside? 80 type A people. Woo! Something happening. Something happening. How many neutrons? 121. Oh my word. We need a lot more neutrons now. We need a lot more ryons to go in there and stabilize that. Okay? All right. So between 21 and 80, we're showing an influx of neutrons that's needed, naturally that's needed to stabilize that repelling force. Okay? They're still stable, mind you, but the tension is getting greater and greater. Like if I keep blowing air into a balloon, the tension is getting greater and greater, and then what might happen? You're going to Hulk out on me? What's that? It'll pop. When you're blowing up a balloon, can't you kind of feel that tension where it's almost on the edge of going, right? You can feel that tension, Okay? So elements, I think the book says, whoops, 83 and above are considered radioactive. I'm reading that. Elements 83 or above is considered radioactive, which means they are going to release energy. What's that? Okay, radioactive. Radiation definition is a spontaneous emission of energy. Spontaneous means it happens by itself, it just goes. Okay, emission means releasing, and then energy. How many of you like exam week? How many are stressed out over exam week? All right. Do you do anything to make you feel better?
I pop bubble wrap.
You pop bubble wrap. All right.
I cry.
What's that? You cry. Okay. So here's that connection again, right? Exam week. You have a lot of tension going on. A lot of tension. Some of us are going to cry. Some of us are going to eat. Some of us are going to do bubble wrap. Some of us are going to punch a punching bag. Some of us are going to run 3 hours.
3 hours.
Maybe 4.
You don't even
You know.
worry about it.
You're only stressed out for the grading, that's about it.
I know. I want you to do well, though. You know, I get stressed out.
It takes things
But when I was taking grad class, or even when I was in college, whether grad class or not, right, we all stress out. So we have this tension, okay? A lot of times that tension, we behave differently, right? We're a little bit more irritable, right? You walk home, you're throwing things, you're kicking the cat, you're yelling at someone, you're just not yourself, right? Okay? You're just not yourself. So you have this tension build up, and then you release this tension through physical activity or through eating or through something. You release this activity. And when you release the activity, you feel better. Okay? This is what's happening inside the nucleus. When these elements are radioactive, there's so much tension inside that they want to release this energy to become stable, to become normal. Okay? So we have this release of energy from the nucleus that we sense as what we call radiation. Does that make sense? There's so much going on inside the nucleus. The neutrons can't combat that tension, so it's going to release it to become stable. It's going to release this energy to become normal. And the radiation is going to be released in 3 different types of radiation. What are the 3 types of radiation? Eating is radiation? There you go. Alpha, beta, and gamma. So the radiation that could be released is alpha. Alpha radiation. Okay, so that's one type could come off. We have beta. And we have gamma. Okay, alpha, beta, and gamma. We won't talk too much about the gamma part. Okay, and alpha radiation is low energy. On the atomic level, it can have an effect, but on a macroscopic level with us, it's not. Our clothes can stop it. A piece of paper can stop it.
Oh, I bet you has something to do with that one.
Oh.
Because there was 25, 3, and 4 notes. Guess what, when you turn it on, who did it? Keep the little things on the paper, little dingy things. It freezes.
Thanks, Ryan. All right, symbol.
Shortcut everything.
Symbol looks like one of the fish symbols for like on the back of a car. You have those Christian symbols. Look like a a backwards fish, or an A for alpha, backwards A for alpha. And here's the cool thing. An alpha particle, as energy is coming off, these particles are coming off with energy. An alpha particle is a helium atom. 4, 2.
Supposed to be backwards there, or you just saying backwards in and then forward?
What?
What?
I thought you said it's a backwards.
Oh, because it looks like it does look like a regular A.
Yeah, it kind of looks like an A.
The first one you did.
They're just kind of, yeah.
Oh, okay. Looks like a little fishy.
Right. So we need to understand that an alpha particle is a helium atom. Okay, that would be important when we get to our equations. What's that? Happens in the sun, exactly. All right, we're good with that? Okay, a beta particle is a high-speed electron. High-speed electron. It's kind of, high-speed electron. And this one has more energy than the alpha particle. More energy than the alpha particle. Can go through your clothes, can go through a paper. Again, macroscopically, it's not going to affect us that much. You know, we're not going to get sick or anything like that. Gamma radiation, you will. Okay. This is kind of cool. In beta radiation, a neutron splits. That's very cool. In the nucleus, a neutron is going to split for beta radiation. It's going to split into a proton and an electron. Isn't that cool? And that's where the electron comes from in this radiation. Symbol for beta radiation is a 0, -1, E for electron. So it's got a mass number, it's got a bottom number here, not really an atomic number. You might also see it as 0, -1, with the funky B and a tail to it. It's like a Greek symbol, okay? But this is the one I'm going to use. Gamma radiation has the symbol nu like that. Looks like a Y.
Can you just draw why do you have to?
That's a Y is fine. Gamma radiation is more like wavelengths. These are particles. This is no particles. It's all waves. A lot more energy. Above X-rays can damage you, can do damage to your cells, mutation. You might have heard of Chernobyl reactors in Russia in 1986. That nuclear reactor kind of crashed. They still have an effect of it today, 37 years later. Okay, pretty bad. You got, if you look, I tried to find videos to show you, to kind of show you the effects of it. I really couldn't find anything decent to show you that did what I wanted to do. But they talk about mutation of babies, mutation of animals. They talk about the death and then the pain and that sort of thing. So the gamma radiation can do a lot of hurt to you. Okay. That's all we need to know about nuclear stability. Now we're going to apply that to nuclear equations, and we're done. Nuclear equations are very easy. Can we get it done in 11 minutes?
Is there no symbol for that? Must be efficient. That's it, okay.
That's it. Okay? Okay, so do you understand? At some point in time in the nucleus, the neutrons cannot stabilize the protons, so the nucleus is going to release energy. And that releasing of energy is an alpha or a beta or a gamma or a multiple of the three. So we want to show that using or writing nuclear equations. Now this handout is not anything you're going to write on or answer. This is, I just want to show you pictures on this one. So on the back side is an article about americium. I'd like for you to read that, just more for information, but you don't need to do anything with it. On this side, I want you to take a look at this. So we have this picture of radium, Okay, and it has little spikes coming off of it, so it's radioactive.
What was it? Spider?
I don't even know if he's awake.
Oh, there it is. His hand moved. He's good. He's good. All right, so take a. Good morning.
That's
He's releasing tension. He's good. So we have this radium with the books up. I should do my Canon.
No, we should have just left. And then like turn off all your clocks when he got up.
Oh, we did that last year, in the Smiths class. There's, this kid fell asleep, and like, it was the end of the hour, so he left all the lights off, because we were watching like a movie, and then everyone left, he closed the doors, and he like, covered up the clock so he wouldn't know what time it was. So then you just saw the kid sprinting.
That's hilarious. All right, try to get this done real quick here, real quick. Help me out. Okay, so we have this radioactive atom here, nucleus. Okay, it has all these protons and neutrons in here. We have the mass number. We have the atomic number. Now, the arrow is telling me what's going to happen. This is going to go through what we call an alpha decay. So that means alpha particle is going to decay, is going to break off of this. So if you look at the picture, we get a chunk out of here, and here's my alpha particle. All right? So this is the energy being released. This is why we get left over. There's a change. When I get done running 3 hours, there's a change in my attitude. I'm not irritable anymore. I'm patient. I'm not short with people. I'm more relaxed. I've got rid of my tension. Okay? So what happened here is that we have all this tension. It's releasing the energy, and it's leaving us with something left over that's a little bit less, more stable or less dangerous. So what we end up with is 222. How did we get 222 from 226 for the mass number? Took out 4 because this is a helium particle, right? So if I do this, the 222 and the 4 gives me 226. The 86 and the 2 gives me the 88. Okay? So here's the rule with the nuclear equations, is that when we have the equation, we have an arrow on separating two sides. The mass number on this side has to equal the mass number on this side. So even if I have multiple substances here and multiple substances here, it doesn't matter. All the mass numbers on one side has to equal all the mass numbers on the other side. All the atomic numbers on one side has to equal all the atomic numbers on the other side. Okay, if you got that, then that's the hardest part. We're good. Okay, but isn't that cool? This is the alpha particle coming off, and it will keep shooting off until this whole thing becomes stable. All right, so how do we write a nuclear equation? Well, let's use uranium-238 as an example. We use uranium-238 as an example, and we're going to do an alpha decay first. So I'm going to ask you to write an alpha decay using uranium-238 as an example. Okay, so I'm going to write 238 uranium. I'm going to draw an arrow. And then on the other side of the arrow, I'm going to write down, just like you have on your worksheet, on your handout, what it's breaking up into. So if it's an alpha particle or an alpha decay, I'm going to write 4,2 alpha, because this is coming off of this, just like your picture. Alpha particle is breaking off of this. Okay, and on your test, I might put a question mark, meaning what is it breaking up into? What do I have left? So here's what I do. I do some mental math. If this is breaking off of this, what is my new mass number? 234 is my new mass number because 234 plus 4 gives me 238, right? The mass numbers added together has to equal the mass number on the other side. My atomic number becomes 90. So 90 plus 2 gives me 92. So this is my new substance. Once I get that far, I look on the periodic table and I find number 90. What is number 90? Thorium, TH. And you're done, that's it. Got it?
So sometimes when they when they found elements, wouldn't that mean sometimes they'd be changing into different names?
If it's radioactive, yes. Yeah. Okay. Let me do one more. Let's do samarium 152. Again, it's going to go through an alpha decay. Write that down and check with the neighbor as I pass this out. Just enough. There we go. Okay, so alpha decay. I'm going to write down my alpha particle. This is breaking off of this, just like our picture shows. So what is my new mass number? 148. 148. What's my new atomic number? 60. What's my new substance? ND. Easy peasy?
Lemon squeezy.
Lemon squeezy. All right, last one.
Someone else say it?
Carbon 14 isotope is radioactive. And for this one, we want to do a beta decay.
No way.
Do the same process, but now using a beta particle instead of an alpha particle. What would this look like? Beta decay, same process, but now we're using a beta particle. What's the beta particle? Ready? Beta particle, 0, -1, E, right? Just from your notes. Beta particle, high-speed electron. Now, what's my new mass number?
14.
14 didn't change. What's my atomic number? 7.
Oh, yeah.
7 minus 1 is 6.
Well done.
And so now we have nitrogen.
Good old nitrogen.
And we're not doing anything with gamma, right?
No, not anything with gamma. Worksheet 1 through 5.
Brought this back.
Only one
No.
through five?
1 through, yeah, on this page, 1 through 5. Not the back side, this is extra stuff.
That's it.
Practice problems 1 through 5. You can do them all if you want.
What's that?
That was for you to have a visual of what was going on. Nope. All right, so 1 through 5,
Quit complaining. Some people wish they could be.
and you have the quiz tomorrow.
Nerd.